Okay, so we're going to talk about estimating the population mean, and it's a similar process, like I said, to estimating a population proportion. But before we do this, we're going to introduce a new distribution. You guys are all accustomed to reading from Table 5 at this point, and that's for the standard normal distribution, and that gave you this table full of probabilities, and you had to kind of read backwards to find a z-score, or if you knew the z-score, you could go look up the probability by indexing it in that table. And it represented the area under the curve to the left of z. Okay, flush that out of your mind, because now we're going to introduce a new table and a t-score for population mean estimating, and it reads entirely differently. So just know that these tables, while you have to consult them for formulas, you read them differently. So we'll get to that in a moment, but first let's just talk about some of the basics, and then we'll do some examples. Okay. Our goal here, just to kind of list the goals of today's lesson. We're going to obtain a point estimate, just like we did for proportions, but we're going to calculate a mean from the sample instead of a proportion. So that's just add them all up and divide by the sample size. Okay, so that's how we'll calculate our point estimate, and that's called X bar instead of being called P hat. Okay, so we'll call this, when we get the result, that's going to be X bar. Okay, we're going to look at the properties of the student t-distribution, and more or less just to describe why we use it. The formula you'll be interested in is the one that calculates the actual it's going to give you the lower bound and the upper bound for the estimation, so the confidence interval. But we will look at just some of the underlying information leading up to that. So I'll kind of emphasize the formula that you're interested in when we get to that. But we will look at the properties. And t-values, that's another example. It'll just show you how their table of data was built. We'll tap into it when we calculate the confidence interval. So at that point, when we get to this fourth objective here, we're going to take pretty much the same concept that we learned for p hat, except we're going to put X bar in the middle, and then we'll subtract the margin of error and add a margin of error to get the lower bound and the upper bound for the confidence interval. And then we're going to also, it's important to know how large of a sample size you need to estimate a population within some margin of error. That gives you more control over what you want to present. If I want to be really certain that you're going to win this state or something, if it were a candidate, that might be more applicable to a proportion, but I want to make sure that that you're going to fill a bottle within a lower bound and an upper bound of the number of ounces or something like that, the average that goes in from some machine. So it depends on the application which confidence interval you build. Okay, so back to the point estimate. Remember, the underlying statistic or the underlying parameter for which we're producing the statistic is the population mean, mu. So that's mu. So we get a sample size n, and we calculate an X bar based on that sample, and what it's trying to estimate is the underlying population mean. For example, Pennies minted after 1982 are made from 97.5% zinc and 2.5% copper. We've got data here that represents the weights of 17 randomly selected pennies minted after 1982. Now, in this case, the underlying distribution, we talked about this before, is a normal, represents a normal distribution. So that's a requirement of this particular process. So if we took all these and added them up to calculate this point estimate, of course, we're going to take each of these, add them together, and divide by how many there are. So we get an X bar from this sample of 17 to be 2.464 grams. So that's our point estimate of the parameter mu. What this tells us is I'm introducing now the student's t-distribution. Okay, so and this formula right here is just kind of describing how t is calculated, and then it tells us that it follows this t-distribution that we're going to go look at, and it's table 7. So that's what it says right here. Now, if you go to your go back to your Blackboard shell, then remember that you've got access to these formulas and tables. So just go click on that and come down here, and there's table 5 that you've used a lot, and here's table 7. So this is what we'll be learning about today. Okay, so t-distribution is a little bit different from the standard normal, and this describes how so. So basically, the key thing to understand is that the dispersion is greater in the t-distribution than it is in the z-distribution. And that kind of falls back to the fact that we have to use a point estimate for the standard deviation. So if our standard deviation is coming from a point estimate, then clearly it's not going to be as accurate as if we've got the actual standard deviation. So it's widened, and that's what makes the t-distribution different from standard normal. Okay, so that's some background stuff. To get into the nitty-gritty of using it, we're going to learn to tap into the table here. So I've gone ahead and copied the table as a couple of slides, but you'll want to know where to get to it. And then we'll also use the formulas. So real quick, the properties of the t-distribution. One thing is that we're going to introduce the concept of degrees of freedom. Now let me just get this kind of said up front. We will always use n-1 degrees of freedom. Okay, it may be possible that you think of degrees of freedom and you're going, oh, what do I want to use? Just start thinking n-1. So we always use n-1 degrees of freedom. And remember, n being the sample size. Okay, so never let yourself be confused about how many degrees of freedom. Just take the sample size and subtract 1. Okay, again, the t-distribution is centered at 0, and it's symmetric about 0. That's just like the standard normal, z. The area under the curve is 1, just like standard normal. The area under the curve to the right of 0 is half, and the area to the left of 0 is half. So appearances are just like a standard normal. The only thing is that as t increases or decreases, so this is, sorry, this last part is just saying that the x-axis is an asymptote, just like it is for standard normal. So much of this is like standard normal. The difference is that you get different values for different degrees of freedom. And that in general, there's more dispersion. Okay, so we'll get back to this slide, but the thing I should probably point out is that we are interested today in this formula. Okay, so this is chapter 9. This was from 9.1, confidence intervals for p hat. You might remember that. This is for 9.2. When we get to 9.3, we'll go to this next bullet. But that comes straight off of that PDF that I just located on your Blackboard shell. All right, so let's get down to some examples here. So just to familiarize you with the table 7, what's different here is that the areas are the column headings. These are not areas like they are on the standard normal and the Z. The Z-scores came from out here and the areas were in here. It's the other way around essentially. You get your area from the top column header. You get your degrees of freedom from the leftmost column, and then the t-value is in the table. Here's the other difference, is that it represents the area in the right of the table. So this is 0.05, that's the area to the right of the t-score that you're gonna find. Okay, probably the easiest way, and there's a second slide because it goes all the way down to 1,000. Let me show you something interesting here. If you look at, once they get past 1,000, they don't bother with any more degrees of freedom. That's because your sample size is getting so large that the law of large numbers kicks in. And as it gets larger, this starts to take on more and more of the standard normal. And by and large, by the time you get past 1,000, they're just going to give you the Z-score. And what's nice about it is that they give it to you in terms of the area in the right of the table. So you could theoretically, for that last section where you were looking up like Z sub alpha, you can come up here and let's say your alpha or your alpha over 2 was 0.025 and you wanted Z sub 0.025. Just go down to the bottom in the last row and it tells you for 0.025 it's 1.96, and that's already converted. It's, if you look that up on table 5, it would say negative 1.96, and you have to remember that's the for the area to the left, so you'd swap that sign. But if you come here and read it, and the alpha over 2 that you're interested in, or the alpha, whatever the application is, just the subscript of Z is one of these, then you're good to go. Just read it directly from here. Plus you have that shortcut table, so they give you a lot of options. Okay, so here's how we construct the 1 minus alpha times 100% confidence interval for the population mean. We've got some requirements here. The sample has to come from simple random sample. It's got to be random sample, and the sample size has to be small relative to the population. So that's the independence rule. And then this time the data has to come from a normally distributed population or a sufficiently large sample size. Okay. And so when we calculate X bar, here's the parts we need. We're going to go look up T sub alpha over 2. So if alpha was 0.05, then 0.05 divided by 2 is 0.025. And then N tells us how many degrees of freedom. So if N was, say, 10, then we would go look up T sub 0.025 using 9 degrees of freedom, because remember it's N minus 1 degrees of freedom. So let's just go do that. Okay, so 0.025 and 9. So what I just described is a T value of 2.262 right here. Okay, and then the upper bound is just, it's just like a margin of error. So you can think now of this part as the E. So it's going to be X bar plus and minus E. All right, so let's put this to work. We're going to look at the pH of rain. So the data shown there represents pH of rain for a random sample of 12 rain dates. So let's just document some of our important values. N equals 12. In Tucker County, West Virginia, a normal probability plot suggests the data could come from a population normally distributed. Well, remember that was a requirement, that third bullet item there. There's certainly not 30 or more, so our data is not large enough. And there's no outliers, so it's not going to destroy the mean, the sample mean. So what we need to do is find the point estimate for the population mean. So we're looking for X bar. A is essentially saying, what's our point estimate? So you could add those up manually and divide by 12, or if you want to punch it into your calculator, just go to your stat edit. And I've already entered these data points into L1, so you can see that I've got 12 of them. So once you got them entered, you can just do a stat calc, one of our stats. And there's our X bar, 4.89. We'll round it to 3 decimal places, so we'll say 4.893. If you look at the formulas of interest, we also need the sample standard deviation S. So let me note that here. Okay, so we're going to plug the S in. So going back to our calculator, that's the nice thing about using this is that, remember that since it came from a sample, we need to use S sub X and not sigma. So our sample standard deviation, we're going to say is 0.319. All right. B is saying let's construct a 95% confidence interval for mu. So basically that's X bar plus and minus E. So what we need is E. And that's the part that we add and subtract. So we need T alpha over 2 times S over square root of N. Oops. Okay, so what is alpha? Well, remember, you can directly determine alpha from the level of confidence. So we've got alpha 0.05. So alpha over 2 is going to be 0.025. So we need, using 12 minus 1 degrees of freedom.
Mr. Cooper?
Yeah.
Where did you get the alpha 0.05?
Okay, so they asked for a 95% confidence interval. And remember that that comes from a 1 minus alpha times 100%.
Oh, okay.
So we have to plug in 0.05 in order to make that 95%. It's just the complement of this in decimal form.
All right.
The next question is going to ask for 99%. That's going to change our alpha to 0.01, but we'll do that later. Okay, so let's go get T 0.025 using 11 degrees of freedom. Okay, so here's 0.025. And there's 11 degrees of freedom. 2.201. Oops, I'm going the wrong direction. Okay, and then we already have our S and we already have N, so E is equal to 2.201 times 0.319 divided by the square root of 12. And if you plug that into your calculator, let's do that. Oops.
So we only use the n-1 when we're finding the t-score?
Correct.
All right.
Okay, so let's take this out 4 decimal places. So we'll put 0.2027. Okay, so we want our lower and upper band is going to be 4.893 plus and minus 0.2027. Okay, so our lower band is 4.693. And our upper band is 5.0957. All right, so our answer for A, or not A, but B, okay, so remember to interpret it if it asks for it. So we're 95% confident that the population proportion is between 4.69 and 5.10. And this is the pH of rain. Okay, so C, I don't know if I want to do this one 100%, but let me just put the parts that are going to change. So since alpha is equal to 0.01 for 99% level of confidence, we need T sub 0.01 divided by 2 would be 0.005. And we're still using n-1 equal 11 df. So let's just go get the new T sub 0.005. Okay, so now we're interested in this. 3.106. So the only value that's changed for our calculation of the margin of error here is 3.106. So I'm just going to substitute that. Now create a different confidence interval. Notice how we bumped up the confidence, but we didn't change the size of our sample. So we're scaling this same number here by a larger value because we wanted to be more certain. We had to be more flexible. So this is going to end up expanding the confidence interval to be wider, and that's not necessarily good. We could do one of two things to improve. We could increase the sample size because then we're dividing this factor by a larger number, thus shrinking it. Or if you decrease the level of confidence, then you'll find that your t value is going to decrease. If you increase the level of confidence, it's going to bump that up. So you have to kind of play with those until you get what you want for your situation. And that's what this last question is basically asking. Part D says, what happens to the interval as the level of confidence is increased? Well, the interval gets wider. Okay. Now we could also be given the information directly. So for instance here, instead of us having to put the data into a calculator and calculate X bar and S, X bar and S could be given to us as part of the question. So in this case, Tootsie Pop, they wanted to answer how many licks to the center of a Tootsie Pop. And this is no joke. This is real stuff here. So in an attempt to answer the question, university student asked 92 volunteers, so n equals 92. Count the number of licks it took before you got to the chocolate center, and the mean number of licks was 356.1. I don't know what 0.1 lick looks like, but so X bar equals 356.1, and standard deviation from the sample is 185.7. So we want 95% confidence. And that implies alpha 0.05. So we need t of alpha over 2 using 91 df, 92 minus 1. So let's go take a look. So 0.025, and we don't have 91, but we got 90, so that'll be close enough. Or you could, yeah, that's close enough. 1.987. Okay, so we're going to take our X bar, 356.1, add and subtract 1.987 times S, 185.7, divided by the square root of sample size. We'll start with the lower bound. Okay, so 317.63 licks. And then you can do a second enter to up arrow your last key in, and then just replace the minus with a plus. It's one way to do it. So the upper bound is 394.57. Okay, that's a pretty wide span. So we are 95% confident that the actual number of licks required to reach the candy center of a Tootsie Pop is between 317.63 and 394.57 licks. Important stuff. Okay. Now the size of n. This time we want to know within some margin of error. So how large of a sample do we need to achieve that margin of error? So now, interestingly, let me just point this out. Notice that it's requiring a z value here, and the reason it's requiring that is because to read a t value, you need a sample size n, and we don't have one. So in the meantime, we need the z value, and we also need s. Wow, that's huge. Okay. Never mind that. So we also need s. Where are we going to get s? Well, we need to have gotten s from some previous sample reading. So we need a little bit of help in order to do this. So we'll need to have obtained a sample somewhere and gotten an S. We won't use X bar from the sample, but we'll use S. And then we'll just go ahead and round to N up. So let's look at a problem here. Now, we didn't look at estimating miles per gallon of 2011 Ford Focus, but let's assume that we did. And we want to know how large of a sample is required to estimate the mean miles per gallon within E of 0.5. So this is our margin of error. And we want 95% confidence, so alpha equals 0.05. Okay, so N equals, well, we got to go look up Z, alpha over 2. And like I said, you could, if you want to do more work, you could go back and find that on table 5, but since the last row of the T table gives us that very thing, see this right here? So, so we're back at 0.025. We already know this is 1.96, but just to verify it here. So 1.96. So we're going to take 1.96. Now, we're going to assume the sample standard deviation from a previously taken sample was 2.92, so that's what's going in for S.
Will that S always be given to us? No problem.
It'll either be given to you or the data that you need to, the sample data you need to calculate it will be given to you. So in essence, yes.
Sure.
And then we divide by what our desired margin of error is, which we said 0.5. And then don't forget to square the result. All right, so since it calculator gives us 131 and some change, we'll have to round that up to the nearest whole number. So we need a sample size of 132. Okay, and that's going to give us the level of confidence we want within the margin of error we want. So that's pretty important. Okay, that kind of summarizes what we want to discuss today. Y'all have any questions before we wrap up? Again, it's similar in a lot of ways to last class, but different in the sense that we have a whole new table with a whole new process for reading. And we've introduced this concept of degrees of freedom. And you lose a degree of freedom by doing things like using sample estimates in place of actual parameters. And that just kind of widens the net a little bit. So you have to hone that in by increasing the sample size or decreasing the level of confidence, mix and match. Okay, do this.